Determine whether a piecewise function is continuous. So for our first example, we are being asked to determine whether the following function is continuous. And we're given a piecewise function where we're going to use 4 minus x squared for all the x values that are less than 2, and 4x minus 8 for all the x values that are greater than 2. So since we are trying to determine whether or not this function is continuous, we are going to have to use our 3 conditions of continuity. But before we can apply those conditions, we have to figure out for which point we are checking the continuity for. So we need to find our a value. And we can find our a value pretty easily. We can see here that our piecewise function is connected at x equals 2. So therefore, we are checking for continuity at a equals 2. Now, before we can check for continuity at a equals 2, let's first go ahead and let's just sketch out our number line so we know where each expression exists on the number line, or relative to a equals 2. Alright, so a equals 2 is the point we're checking for continuity, so we'll throw that in the middle. And let's see, when x is less than 2, so when x is less than 2, or when x lives on this side of the number line, we can see that we're going to use the function 4 minus x squared. And when x is greater than or equal to 2, so since it's equal to 2, we'll put the closed circle at the 2, and then we'll shade in everything that's greater than 2, which is to the right. And that set of x values will be 4 minus 8, or excuse me, 4x minus 8. Alright, so now that we have that figured out, we can come in and we can look at our conditions of continuity. Now let's remember our first condition is that f of a is defined. So all that means is we need to take our a value, which is 2, plug it into our function, and see if it outputs a y value. So we've already said that our a is 2, so that means we're going to be looking for f of 2. Now we just need to figure out which one of the pieces of our piecewise function includes x equals 2. And we can see here that the function that includes x equals 2 is going to be 4x minus 8, so that's what we're going to be plugging the 2 into. So 4 times 2 minus 8. And that's going to give us 8 minus 8, which gives us 0. Now this is sometimes a trap for folks because like, oh, f of 2 is 0, so therefore it's not defined, because usually 0 means a bad thing. But remember, 0 represents a number. So all this is saying is that when x equals 2, the height of our function is 0, meaning it's on the x-axis. So that means that the point is defined, so this condition is satisfied. Alright, our second condition is that the limit as x approaches a of f of x exists. Which means we're going to have to look at the two one-sided limits of this particular two-sided limit. So we're going to take a look at the limit as x approaches 2 from the left, and we're going to take a look at the limit as x approaches 2 from the right. And as we can see from our number line, as we approach 2 from the left-hand side, we're going to use the expression 4 minus x squared. And when we approach 2 from the right-hand side, we're going to use the expression 4x minus 8. Now, since both these expressions are polynomials, we know that we can use direct substitution. So that's going to give us 4 minus 2 squared, which is going to give us 4 minus 4, which gives us 0. So our left-sided limit exists. Now we just need to check the right-sided limit. So same thing, 4 times 2 minus 8, which will be 8 minus 8, which will give us 0. So therefore, the limit from the left does equal the limit from the right, which means the limit as x approaches 2 of f of x exists, and it exists at 0. So our second condition is satisfied. Now our third condition says that we need the limit as x approaches a of f of x to equal f of a. Remember, we want the intended height to be the actual height. Let's see, we just discovered that the intended height is 0. And from the first condition, we determined that the actual height is 0. So therefore we can see the actual height is the intended height. So our third condition is satisfied. So what does this mean? Well, this means that f of x is continuous at x equals 2. Boom, boom, boom. Done. We proved it by using the three conditions of continuity. Alright, so in this example, we want to do the same thing. We want to determine whether or not our piecewise function is continuous. And this particular piecewise function is a little bit different because there are three pieces. But the process is the same. First thing we want to do is we want to figure out what points we're trying to determine the function's continuity at. And for this particular piecewise function, it appears as though we're going to have two. We're going to have one a value at -3, and we're going to have another a value at -1, because that's where our pieces hopefully will connect. So we're going to have to check for continuity at a equals -3 and a equals -1. So we're actually going to have to do 6 conditions of continuity here, 3 conditions for each a value. But before we get into that, let's plot all these pieces on our number line to help us identify the limits later on. Alright, so drawing the number line here, we're going to plot the 2 points, which are -3 and -1. And now let's see. When we are less than 3, we're going to use the expression x minus 1, and that actually says less than or equal to, which means we're going to include 3. So I'll just go ahead and shade in this area here. And this is going to be x minus 1. Then, when x is greater than -3 but less than or equal to -1, we're going to have our middle guy. So we can come shade in this area. And this is 1 minus x. And then our last expression is when x is greater than -1. So then we can just shade in this final area. And this would be the expression 3x plus 3. Alright, so now we have to go through and do the set of 3 conditions of continuity for each of these a values. So I'm just going to come in and kind of break up my screen here and kind of split it into 2 pieces. One for a equals -3, and one for a equals -1. Alright, so let's see. Our first condition is f of a defined. So, in our first side here, we're looking at when a is equal to -3, so we're looking at f of -3. So now we just need to figure out which expression we're going to plug -3 into. And as we can see, -3 exists with the red, which is our x minus 1 function. So we'll plug the -3 into that, so we'll have -3 minus 1. And let's see, -3 minus 1 is -4, so this condition is satisfied. Moving on to our second condition now, we need to show that the limit exists. So the limit as x approaches a of f of x exists. Alright, so that means we're looking for the limit as x approaches -3 from the left, and we're looking for the limit as x approaches -3 from the right. So going up to our number line, we can see that when we're approaching -3 from the left, we're going to use the expression x minus 1. And when we're approaching -3 from the right, we're going to be using the expression 1 minus x. And since both these are polynomials, we can use direct substitution again. So let's see, we're going to get -3 minus 1, which gives us -4. And then let's see, we're going to get 1 minus -3, which is going to give us a +4. And then, as we can see, our limits do not go to the same spot. These two limits show us that there is a jump discontinuity at x equals -3. So therefore, f of x is not continuous at x equals -3. And boom, there we go. Because it was not continuous, we actually got out of doing that third condition because we failed. So boom, done, not continuous. Moving on to our next a value, this time a equals -1, and we'll do the three conditions again. So does f of a, or excuse me, is f of a defined? So just like we did before, we were trying to find f of -1, so we just need to figure out which expression includes x equals 1, excuse me, x equals -1, and we can see here that the blue guy does, and the blue function is 1 minus x. So we're going to substitute a -1 into that expression, so we're going to get 1 minus -1, which is going to give us 2. So our first condition, satisfied. Next up, we want to check the limit. Does the limit as x approaches a of f of x, does this exist? And as we know, we have to check both the left and the right-hand side. So we're going to be looking at the limit as x approaches -1 from the left, and the limit as x approaches -1 from the right. Now we just need to figure out which function we're going to use for each side. As we approach -1 from the left, we can see we're going to use the expression 1 minus x. And when we approach -1 from the right, we're going to be using the expression 3x plus 3. And we can see that both of these expressions are polynomials, so we can do direct substitution again, which means we're going to get 1 minus a -1, which will be 2. And then for the right-sided limit, we're going to get 3 times -1 plus 3, and that's going to give us 0. So unfortunately, just like with a equals -3, our limits do not go to the same intended height, which suggests there is a jump discontinuity. So just like with a equals -3, f of x is not continuous at x equals -1. So there you go. For this particular function, we have two discontinuities, one at x equals -3 and one at x equals 1. All right, for our last example, we're going to do the exact same thing. We're going to determine whether the following function is continuous, and we're given a three-piece piecewise function here. So first, we're going to have to identify our a values, and since we have a three-piece piecewise function, kind of sounds like I'm saying a three-piece suit. Oh, it's a nice and fancy function. Since we do have three of them, we know that we're going to have two a values. We're going to have one a value at a equals -4, and another a value at a equals 0, because again, that's where these functions are hopefully going to connect. So a equals -4 and a equals 0. Next, on to our number line. So zoop, number line, -4 and 0. All right, so let's see. So the first piece, 1 minus 3x, these for our first piece, 1 minus 3x, we're going to use this function whenever our x values are less than or equal to -4. So equal to -4 means I'll include that point, closed circle, and I'll shade in everything less than it. So that'd be 1 minus 3x. Then for our next piece, -2x plus 3 whenever x is greater than 4 but less than or equal to 0. So we're including 0 in that piece. So we'll come, we'll shade, done. And -2x plus 3. And finally, I wonder where x plus 3 is going to go. Maybe in the last piece of the graph it isn't shaded. I don't know, maybe. But yeah, here we have x is greater than 0, which is that last piece that we have left to shade. No way. Never would have saw that coming. All right, and then we can see that this section will be x plus 3. All right, and again, we do this number line to help us see and evaluate those one-sided limits simply. All right, so again, just going to divide this up into two sections. One for a equals -4, and that kind of looks like a 9. A equals -4, and then the other side for a equals 0. All right, so three conditions of continuity time. Is f of a defined? All right, so our a value here is -4, so we're looking for f of -4. So now we just need to figure out which function do we plug -4 into. Well, we plug it into the function that includes -4 in its domain, which as we can see is the red function 1 minus 3x. So we're going to have 1 minus 3 times, and instead of x, we're putting the negative 4. And then we can simplify this to, let's see, the negative 3 times negative 4 is 12. 12 plus 1 is 13. All right, so great, satisfied. F of a is defined. Moving on, let's check about the limit. Does it exist? Meaning, does the limit from the left equal the limit from the right? So we're going to be looking at the limit as x approaches negative 4 from the left, and the limit as x approaches negative 4 from the right. And as we approach negative 4 from the left, we can see we're going to be using the expression 1 minus 3x. And when we approach negative 4 from the right, we're going to be using the expression negative 2x plus 3. And both of these expressions are polynomials, so direct substitution time, let's hit it. So we're going to have 1 minus 3 times negative 4, which is positive 13. And then for the limit from the right, we're going to have negative 2 times negative 4 plus 3, which is going to be positive 8 plus 3, or 11, and uh-oh! Our limits do not meet at the same height, so therefore, condition 2 fails. So our function is not continuous at x equals negative 4. All right, and then last three conditions for a equals 0. First off, f of a is defined. Let's check it out. In this case, our a is 0, so we are looking for f of 0. So I just need to figure out which one of our pieces has a domain that includes x equals 0, and from our graph we can see it's the blue one, or negative 2x plus 3. So we'll have negative 2 times 0 plus 3. And that's just going to give us an output of 3. And I really need to work on making my 3's look, you know, like 3's and not backward C's. 3. So boom, satisfied. Awesome. Next up, does the limit exist? And you might be asking yourself, Kuhlman, why do you write the conditions every single time? Isn't that just painful? And yeah, it is painful. However, by writing the conditions every time, it helps me memorize what they are. Repetition, repetition, repetition. So this is one of the ways that I try to, one of the strategies for studying. Always write out the conditions or the definitions of the formulas to help, get it to stick in your brain. Anyways, limit exists means we're checking the limit from the left and the right of 0. So limit as x approaches 0 from the right, and the limit as x approaches 0 from, actually that's the right, I want to make the other one left. Done. There we go. So as we approach 0 from the left, we can see that we're hanging out in blue territory, so we'll have negative 2x plus 3. And then when we are approaching from the right, we're in green territory, so x plus 3. And then these are polynomials, so direct substitution. So we're going to get negative 2 times 0 plus 3, which equals 3. Woo! Next limit, 0 plus 3, which equals 3. Oh, would you look at that? So therefore, the limit as x approaches a of f of x equals 3. And our second condition, that was supposed to be a check, but doesn't look like one. Let me redo that. So it looks as though our second condition is satisfied. On to our last condition. Does the limit as x approaches a of f of x equal f of a? And I've run out of room here, so I'm just going to use the arrow. And we said our limit was equal to 3. Our f of a was equal to 3, so therefore, boom! Satisfied. So that means that our function is continuous at 0. It's just not continuous at 4. Now where can I fit that in? F of x is continuous at x equals 0. Alright, and there you have it, folks. using the conditions of continuity to determine whether or not piecewise functions are continuous.